Okay, hello. Well, I'm Nonia Vaquero, and I'm going to give a talk about an ongoing project that I started some months ago while I was doing an internship in Riken. So this is a project in collaboration with Lucas Broers, Tomonori Shirakawa, and Seiji Junoki, and is called Classical Simulation of Subspace Quantum Diagonalization, a case study on Fe2. And this is, slightly related with the previous talk. So first I'm going to do a quick introduction. So, well, if we want to calculate the ground state energy of a molecule of, let's say, 2k spin orbitals and n electrons, then we have a first good approximation, which is the Hartree-Fock, which is just placing these n electrons on the lowest energy orbitals. But if we want to improve our energy approximation, so we will need to take into consideration all the, more configurations, which the number of configurations is the binomial coefficient of these 2k spin orbitals with these n electrons. So especially in highly correlated systems where the Hartree-Fock is not a good solution, we need to take into account more configurations. So the exact solution is given by this linear combination of all possible n electrons later determinants, which would be given by this expression. But we know that solving this is not possible for big systems, since this is a huge matrix, as we just heard about. So we have to think about clever ways of finding a good subspace in which we will diagonalize our Hamiltonian. So in theoretical chemistry, there are several methods. For example, CISD, where we just use singles and doubles configurations, assuming that those will be the ones that contribute the most, and we just discard the rest of them. But so there are several ways of doing this and several approaches, and this is where we use to introduce the quantum computer. So we say if we can prepare a quantum circuit that has some kind of overlap with the ground state, so when we sample from this circuit, the probability distribution we get is similar to the probability distribution of the full CI solution, of the exact solution, then the bit strings we get when we take these samples will be the most important ones. So we will be able of preparing a good subspace in which we will diagonalize our Hamiltonian. So this is this is the main idea of this subspace quantum diagonalization method. And my research project in Riken was about applying this method, but using it for testing a simulator that is called ORCA, which was developed by Lucas, a postdoc in Riken. So ORCA is a simulator that simulates quantum circuits. So my objective was to use this to the part that would be done in the quantum computer. So do this with ORCA in order to test the proper functioning and the limitations of the simulator. So it is very useful to have classical simulators of quantum circuits, because we always need this for testing our algorithms, to study noise effects, or just for benchmarking. So this was my project. Okay, I'm going to explain a bit how ORCA works. I'm not an expert on this still, but I will try to explain the main idea. So the idea of this is to do a mapping of the Pauli strings to some binary indexes in this way. Just the identity would be 0, 0, the x will be 0, 1, the 1, 1, 0, and the z 1, 1. So we can rewrite the operations of these Pauli matrices in terms of bitwise operations. So in this case, for example, the product of these two Pauli matrices would be given by this expression, where we have the exclusive or bitwise operation, which is easy operation, and this to recover the phase, that is just a function that is given by a table like this, where we will just have to look for the number and convert it to decimal basis, and will give us the phase. So, for example, this product, we just do this mapping where we just rewrite our matrices, which doing the exclusive OR operation gives 1, 1, which is the set, and then introduce the phase. So we look in the table the j and the k, and it gives us 1, 1, which is 3. So we just have to do this y to the 3, and we will recover the product. So we can do this with the rest of operations, like the commutator and anti-commutator. So we don't need to do the exponentially large Pauli matrix multiplication. So we can just use bitwise operations to recover all the algebraic structure. And this, well, I have done this only with 2 Pauli matrices, but we can do this with long Pauli strings. So, well, so using this simulator, I was simulating quantum circuits and then doing quantum subspace diagonalization. So for testing the results, I was using the result from this paper that is one of the largest demonstrations of this algorithm. And in this paper, they simulate 3 different systems, the N2 dissociation, 2Fe2S2, and 4Fe4S4. So in this paper, well, this is a summary of the algorithm, but the main idea is that we first prepare the quantum circuit, then run the quantum simulation and sample, apply configuration recovery, which is just a post-processing method for recovering some of the bad samples we get from the noisy quantum simulation, then prepare batches, diagonalize the Hamiltonian in each batch, and with the results, we collect the new orbital occupancies and perform, again, configuration recovery in like a kind of a loop until we get a good energy. So the ansatz that is used, that I told you before that must have some overlap with the ground state, is this LUCJ, that means local unitary cluster Jastrow, which has 2 orbital rotations and 1 Jastrow part, which are density-density interactions. And this is a hardware that is good for implementing in the quantum computer because these rotations only have same spin neighbor interactions. And the entanglement between the different spins is in the Jastrow part. So these interactions of different spins depends on the layout of the circuit. So for example, here we would have the alpha, that is the red, beta is the blue, and then the different spin interactions are every 4 qubits in these green parts. So the parameters from these ansatz come from a classical calculation, come from coupled cluster calculation. So this is the ansatz that is used in this algorithm. And these are the results they got from the paper. Here we can see an energy variance extrapolation, and this is a DMRG result, so the objective is to reach this result. The crosses are some HCI, which is a classical algorithm calculation, and the dots are the quantum results from the quantum computer. And we see that they reach, in this case, the MRG values. So this is, well, they get good results. For this system, which is the Fe2S2, they have 20 orbitals and 30 electrons and use 45 qubits. So the size of the Hilbert space is 10 to the 8. And the number of different samples they got when they sample from this LUCJ circuit is almost 2.5 million. So then what I did was using this Orca that Lucas implemented in the Fugaku supercomputer. So he made like a fully parallelized version of this simulator. This is the circuit we implemented for the Fe2S2 and with the one that was simulated classically. Using 511 processes, it took 7.5 hours to simulate, and we get 2.39 million different samples, which is quite similar to this number that they got from the quantum computer. And then we did the same of taking different batches and diagonalizing in the Hamiltonian in every batch. And we got that using this classical simulator, we reach also, doing this energy variance extrapolation, we reach also the MRG values almost. And the energies that we got were slightly better since we reached minus 116.5 Hartree, and theirs are a bit lower. This would be 0.1 would correspond to this 0.5, so their energies are a bit lower. So these results were pretty good. And then the next objective was to simulate the other system they have in the paper, that is the Fe4S4, which now, instead of having this Hilbert space of 10 to the 8, we have 10 to the 15, since the number of orbitals and electrons is bigger. But, well, the first simulations I was running were 2,048 nodes, so using 16,000 processes. And the Hilbert space that Orca reached for simulating was 10 to the 11, and then the simulation crashed. So this is a problem because the biggest simulation that Lucas was able of performing in the Fugaku with Orca was 1 trillion Pauli strings. So it is not possible to simulate this system with Orca. So we are trying this backpropagation approach. This is something I'm trying right now, which consists of, well, this is the circuit for this Fe4S4, and this is the first rotation, the just throw part, the second rotation, and this is one final rotation that is added. So taking these two last rotations, cut here the circuit, and simulate only these two parts, including this entanglement, this different spin interaction part, but the last two rotations, implementing them as rotations, but classically rotating the Hamiltonian. So we can take all these gates and put them in the Hamiltonian, yes, just rotating the Hamiltonian instead of the circuit. And, well, this is something I will be doing in the future and testing. For now, simulating only half of the circuit is possible with Orca. So if this works, it will be possible to finish the Fe4S4 simulation. And, well, this is more or less everything. So the conclusion would be that Orca works for simulating quantum circuits, since we got the good results for Fe2S2. And it's useful in these middle-sized quantum circuits, but we need some different approaches when we want to simulate bigger circuits. And then on future work with this includes some orbital optimization and noise study using this simulator. So, yeah, so thank you everyone for your attention. Yeah.
Thank you, Nonia, for the nice talk. We have, and also for staying very well in time. So we have occasion for our questions. Please.
Hi, I would like to ask, how do you deal with the rotations in Orca? Because you explained that you can compute the action of Pauli matrix efficiently, and I agree. But what happens with the rotations?
You can decompose them into Pauli strings and then compute them. You just need to translate every operation to Pauli strings. Yes.
But that gives you a tree that grows with different layers. Am I right? And essentially, you have to keep track of exploding number of terms, but you can truncate. So you are truncating at some point, I guess. Or what are you doing in that?
Yes, that's like for small circuits, we are able of doing it exactly, but there exists some truncation method where the Pauli strings that have lower coefficients just truncate a bit, and you can. I have done some tests, and it works also very well, truncating some part and removing it every few steps.
So for your results, no truncation needed? Because I don't consider your circuits small circuits.
No, yeah.
Okay.
No, for this is full no truncation, yeah.
Okay, thank you. Impressive.
More questions? Yeah.
Thank you for the talk. So the the difference between your simulation and what they got experimentally, can it be explained by the noise on the real hardware? And if then, can you estimate if it's sampling noise or decoherence noise that is have you tried to put some noise in your model also?
Okay, there is one thing is that the results between the results they got and mine, the basis set is different. So I got good results, but I would have to check. And yeah, so the plan is with this truncation, we lose some fidelity. So we would like to see if the noise effect is similar to this truncation in some way, so we can study this, but we have not introduced any noise, but I guess we could, yes. But we have not looked into that still. Yeah.
Thank you. So I see no more questions. If there are none, then let's thank Nonia again.